Next up, we have Mark Penning from JPL with the Farside seismic suite. All right.
Hi, everyone. Thanks for the invite. It's great to talk to a group like this. This is the full list of authors, which is really just the proposal team right here. You can see on the list here, there's a lot of seismologists on this list, and also some great technical people that are going to be delivering this instrument suite to Schrödinger crater on the far side of the moon in the PRISM-1B mission. Let's see here. Okay, so this is kind of the whole talk in one slide. I'm not going to talk about everything on here, but when you go back to the recording and look and see what's there, you can see the whole story in one slide if you're interested in. And so what we're doing with Farside Seismic Suite is we're delivering a couple seismometers, a vertical component, very broadband seismometer, which is the most sensitive seismometer to fly on a planetary mission, and also a capable compact 3-component short period seismometer. And these are both based on instrumentation of the InSight mission, which is operating on Mars right now. In fact, the VBB is actually using a flight spare from the InSight mission. And we're putting all of these inside a thermal enclosure that has its own independent command, power, and communication system. So effectively, we're a CubeSat without propulsion. And the idea is that we outlive the commercial lander, continue operating through the night and recording data, communicate during the day, and last for a nominal mission of 4 months in order to record the moonquakes we want to see. And we're aiming at 3 primary science goals in this process. We're trying to look at the far side seismicity, which has never been analyzed because all the Apollo data comes from the near side, and look at implications thereof. We're also looking at the local crustal structure underneath the Schrödinger crater and linking that into global crustal models. And finally, by putting such a sensitive instrument out there, we can record the background seismic noise better than has been possible in the past, which can be linked to micrometeorite impact rates. So those are the 3 main science goals. So now that you know the whole story in advance, let's step back and think about how we do seismology on the moon. It's very different than Earth seismology in a lot of ways. So on over here on the left, I've got 2 seismograms that are both 1 hour long. One is from Earth, one is from the moon. Same time scale, similar sized events. And you can see that the moon is very, very different than the Earth. So on the Earth, we get nice, clean arrivals that give us this nice spike here showing up. On the moon, the scattering, the seismic scattering is intense, and everything oscillates for long periods of time, an hour or hours. And this adds a lot of complication to how you do seismology on the moon. The Apollo measurements, of course, were only made at near side landing locations. So by taking these modern sensitive instruments on the far side of the moon and adding in modern digitization, I mentioned digitization here because I show a recording of a small moonquake here at the bottom, which shows the limits of the I believe 7-bit digitization used by the Apollo instruments, where a lot of small moonquakes look more like barcodes than seismograms. And this was a fundamental limitation of what could be done for the small events in the background noise for Apollo instrumentation. So we're really getting a chance to explore a lot of new ground here in this Farside mission. Just in a little more detail here, this is plotting the major seismicity locations as recorded by the Apollo stations during the 70s. And all of these circles here are locations of deep moonquakes. These happen hundreds of kilometers deep, and they tend to happen in repeating clusters. So they happen over and over again at repeatable times in the tidal cycle. And then the blue stars are shallow moonquakes, which are the larger quakes that happen once every several months or so. And you can see the orange box is highlighting the near side of the moon. Basically, all of the seismicity observed is on the near side, with the exception of a couple deep moonquake clusters that move over to the far side. And so the question we have to ask is there a fundamental difference between near and far side, or is this simply an artifact of the detection capability of the Apollo instruments due to deep mantle attenuation, not letting us see far side paths as well? And so by going to the far side, we can directly record far side seismicity, as well as recording or not the known repeating deep moonquake locations on the near side, which lets us constrain that deep mantle structure and understand what we're looking at in a much more clear way. Schrödinger crater is a fascinating site. I mean, you could over here you can see it's just a beautiful crater with a nice peak ring. It's very clear and sitting right on the edge of the South Pole Aitken Basin. So it's a beautiful crater within a larger crater. It's got smooth floors that are likely impact melts. It's a really interesting location in and of itself. And with our recordings, we should be able to look at techniques like receiver functions, which look at conversions of stuff coming through the crust underneath the site. This is some example of some work we've done on Mars like this, and similar work has been done with the Apollo records, but we are looking forward to getting this with modern clear instrumentation. And there's lots of different ways we can try to look at the local crustal structure, which then lets us think about Schrödinger crater itself, but also link into the larger gravity-derived models for the whole lunar surface. The background noise is also a really important thing to say. As I said, the Apollo instruments were actually limited by that coarse digitization. So we didn't record the background noise in most places. We just got the instrument noise. But the vertical VBB is these two blue lines. These are estimated sensitivity and displacement compared to Apollo. So we're pushing down the noise floor of the instrument itself, which lets us hopefully measure the lunar noise floor, or at least put a new lower upper bound for what that lunar noise level is. And the prediction is that noise level is actually driven by the more or less continuous impacts of micrometeorites. So this lets us directly link to the micrometeorite impact rate, which is actually not all that well constrained. And of course, that's a pretty important goal for understanding if we're looking at long-term human safety for human occupation of the moons, because those little micrometeorites are going to be impacting everything on the surface. One of the first questions that always comes up is you may have noticed in the pictures that the package is sitting on the lander deck, and we'll be recording through the lander. If for those who have paid attention to planetary seismology, both the Viking mission and the InSight mission before deployment taught us that deck-mounted seismometer is a problem, and that is true. So here's the seismometer on Viking, which never actually recorded a Mars quake, or possibly only recorded one. And but we did some analog experiments sticking seismometers on the deck of the Curiosity rover engineering model in the Mars yard at JPL, and another one immediately below, and across the frequency band that starts below the lowest resonant frequency of the lander and down to 30-second period or so, we actually got very clear coherence between the two records. The recording on the deck was effectively identical to the recording on the ground. It could record seismicity on Earth quite clearly. But one thing we noticed interesting is during the day, we had some decorrelation because of the activity of the air conditioning in the hangar where the engineering model was stored. And this is totally analogous to the problems faced by Viking and InSight, which were related to wind. Of course, that's not a problem on the moon. There is no wind. However, we will be having to deal with thermal noise at dusk and dawn. This is analogous to the thermal moonquakes that are actually measured by Apollo instruments that were put well away. But we'll lose some data around that time, and we'll lose some data at high frequency above the resonant frequency of the lander, but we should be able to record good data across a broad frequency band and during the times away from large temperature changes. A little bit more about the seismometer. This is a flight spare, very broadband seismometer from the InSight mission, rotated to measure vertical instead of at a tilted axis. With a spring change required to account for the different gravity on the moon compared to Mars. This is contributed by CNES in partnership with IPG Paris. So this will be delivered and give us very high sensitivity. The 3-component short period seismometer looks like this. It's set up in a Galperin configuration with 3 tilted seismometers that all measure a tilted axis, so they're all identical, but you can combine them to get the full 3-component system. It's a new build, but it's based on the InSight heritage. And this one will be directly delivered by Kinemetrics Incorporated, which is a leading manufacturer of seismometers and seismic data equipment, and is in collaboration with Oxford and Imperial College London. And this is a micro machine silicon system. Just a little bit more about the sensitivity here. These are some plots of this compared to what we believe our requirements are to get the number of moonquake recordings we're expecting. And compared to some of the Apollo data here, and we're really looking forward to getting this high quality data on the moon. The package design, as I said, is a pretty innovative system, and it's basically a box within a box with spacerless multi-layer insulation put in between the 2 boxes, which gives us excellent thermal control. And that lets us stay warm through the night. So the batteries function well at the warm temperatures, and we can maintain operation through the night, running at about 5 watts, which to keep the instruments running. And all they're doing is passively running and recording the data. And then during the day, the command and data handling system kicks in and does comm activities, et cetera, communicating with the planned relay satellite. And that all of the command and communications and power systems are based on Marco flight spares, and they'll be delivered by the group led by Jamie Cutler at the University of Michigan. I'm flying through this, but let's see here. So the one question you might ask, given what I'm talking about here and what Bob Dribb's going to talk about next, an interesting thing here is that this PRISM 1B mission to Schrodinger crater includes Farside Seismic Suite, which has the 2 different seismometers. There's also Litmus, which will include a magnetotelluric measuring system and a heat flow measurement system, and Lucy, which is led by Stuart Bale out of Berkeley, which will have a lot of magnetic measuring equipment, electromagnetic measuring equipment. And by combining all of these, we've actually got most of the primary instrumentation, or something analogous to the primary instrumentation proposed for the Lunar Geophysical Network, which was recently re-explored in a planetary mission concept study led by Clive Neal last year. And I think it's worth mentioning that this is exciting, because this means this is effectively somewhat of a test node for a potential future lunar geophysical network. It has, and we've carefully defined some great science goals that we can reach with a single relatively short-lived station, but a long-lived network still, I think, is an important goal for the future of exploration science on the moon. We with a network, we can locate events much more reliably and have many more events to look at. And the long-lived network data samples the whole moon, and whereas we're only focusing on the one area we can really access with the Schrodinger crater site. but this, you know, this idea is that this can be a key pathfinder for LGN. So we can look at some of the trade-offs of an undeployed package. Obviously, Insight has taught us that deploying to the surface is helpful. But you know, this lets us quantify the trade-offs of that, because there are big cost differences between having a whole robotic system for deployment or remaining mounted on the lander. And this lets us demonstrate the instrumentation, and the system we've got for night survival and long-term operation is a system that could be used either within the context of LGN or in future PRISM missions with other instrument suites. So this is exciting in a lot of those ways. So just to summarize it all up here, Farside Seismic Suite were designed to go to the moon, outlive the commercial lander delivery system, and we're looking at some key lunar science from the far side of the moon. And so we're looking at far side seismicity rate. Is there a difference between the near side and the far side, or is this due to deep mantle attenuation? Looking at the crustal structure at both local and global scales, and looking at this micrometeorite impact rate through the background seismic noise. This is the combination of instruments are very complementary on PRISM 1B, and so I'm really looking forward to have this geophysical package delivered to the far side of the moon. Okay, thanks a lot.